So we are like now. So the can people work. It's okay. Okay, now let's see our profile. 82 questions. Yeah, it has not solved. So let's make it 92. In fact, 95. Let's aim for 92 at least. So today we should be solving some of these questions from here. Like we'll try to complete this. This is premium, so I will not touch this. We'll be trying to complete this. Three of them. There's four of them. This is again this needs some concept. Recursion, we'll do that later. Complete these. We'll try to complete all of this easy. 4, 5, 6, 7, 8, 9. We'll be completing some SQL questions and try to hit this up to 95 or 100. We'll see. So we'll try to hit this 95 or at least like 95 or if we have limited we can do more questions. So let's start. So let's go to adjoint element 2. I tried this I guess. I'm not sure. Build an array of length n. Find all elements that appear more than. Well, by the way, guys, I'll be staying for 6 hours. So that's 2, 8. Yeah. So whenever the 10 questions are done, I'll end this video. So then I've already had my lunch. So okay. More than n by 3 times. Okay. So alright. This one I'll do later. Okay. So, so could you solve the problem in a minute? And so this easy to solve this actually. So 1 comma 2 output is 1 comma 2. So what is 2 by 3? I think this row division. So it should be 1, but let's make it 0. So greater than 0 is 1 and 2. So we can actually solve this using hash mark or a dictionary. Let's take example 2, 3, 1, 5, 5, 7, 3, 5, 3, 7. an array. Now, solve this. Let's name this. Name this. So we can take a dictionary. Then we can, I think, we can store the key value there. Like, um, let's say we have let's say three. Two is not there. That's one. Two is not there. Two and one. Three again. Now this will become two. That's two. One is not there. So one five. Five is not there. One five again. So two. Seven is not there. Seven one. Three is there. So three will become three. Five is there. That will again become three. Three is again there. Three will become four. Seven is again there. Seven will become two. So the total n is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So what is 11 by 3? 3, 3 is 9, 3. So it's greater than 3. So greater than 3 is 3. Yeah, this is greater than 3. Yes. So this is one of the answers. This is equal to 3. I don't think this is 1. So we should go after that. So we can just compare the values and both the values greater than 3. You can return that. That is the answer. So straightforward. Done with hash map. Uh, okay. Could you solve this for a linear time and then 0 O of 1 space? So how to solve this in O of 1 space in hash map approach? So O of 1, I don't think I can solve this. O of 1, 2 pointer 1. But you need an array to store the index. Sorting, we can change sorted, but sort is not linear time and log n. So this dictionary is taking up n space because n elements, so it's taking an extra space. So space is equal to O plus n because it's taking time is n different. It's taking a dictionary of size n. Time is equal to it's just a lookup, right? So time will be so I mean time is not is linear time like O of n because you iterate through the array once and then you store the numbers. So what is now? So how can we solve it? So with hash map, with the sorting, time will be O of n log n. This again, not linear time. Space will be less, so it's fine. Space is again, space is O of n. Um, Two pointer, I don't think you can start using two pointer. Two pointer is again spaces over now. Time is again so and into and minus one is equal to that. So time is equal to that times two pointer also is not coming. Two pointer. So what else? Let's see the solution because it's about that way of learning. Let's see the solution. Let's do force. Okay. Okay. It's going to count this time space. Same like this is the dictionary of the same thing. Sorting is also then spaces. Time is open or is open or yeah. Right. If you use lots of something like that. One more thing algorithm. This is time cognitive linear. This is what we want to learn. One more voting algorithm. One more voting algorithm. This is also something we can learn. Let's first learn the algorithm.
Hey everyone, welcome back, and let's write
Connect my earphone.
some more neat code today. So today let's solve the problem majority element 2. I highly recommend you solve the first version of this problem before trying to tackle this one, even though this one is slightly different and the solution definitely is a bit different. But we're given an integer array of size n and we want to find all elements that appear more than this many times. Now this is the floor. It's not written super well, but basically taking the length, dividing by 3, and rounding that down. So what does that mean? If you took a number like 9 and rounded that down, well, you don't need to round it, right? It divides pretty evenly and you get 3. So we want and this many times. Now this is the floor. It's not written super well, but basically taking the length, dividing by 3, and rounding that down. So what does that mean? If you took a number like 9 and rounded that down, well, you don't need to round it, right? It divides Hey everyone, welcome back, and let's write some more neat code today. So today let's solve the problem majority element 2. I highly recommend you solve the first version of this problem before trying to tackle this one, even though this one is slightly different and the solution definitely is a bit different. But we're given an integer array of size n and we want to find all elements that appear more than this many times. Now this is the floor. It's not written super well, but basically taking the length, dividing by 3, and rounding that down. So what does that mean? If you took a number like 9 and rounded that down, well, you don't need to round it, right? It divides pretty evenly and you get 3. So if we had an array of length 9, we want all the elements that appear more than 3 times. First version of this problem was taking n and dividing it by 2. And that is the majority element, like an element that takes up more than half of the array. But this time, we want elements that take up more than a third of the array. If you were to take a number like 10, which doesn't divide evenly, but you still round it down, we would get 3 as well. So we want elements that appear more than 3 times, and in that case, we'd get 4. 4 is more than a third of 10. So that's kind of the idea. But in terms of the solution, it's not super complicated. We could very easily solve this problem with a hash map, couldn't we? Just count the occurrences of every single element and then afterwards go through every element in the hash map and just check, is the count greater than n divided by 3? Is the count greater? If it is, then we add that to the result, and if it's not, we don't add it to the result. Well, first of all, you should recognize that the output is not going to be arbitrarily large. I said that we want elements that like take up more than a third of the array. How many elements do you think can do that in a single array? Probably no more than 2 elements. Suppose we had an array of size 4, and let's say we have a 1 and a 1 and a 2 and a 2. These both would be the result. How many elements do you think can do that in a single array? Probably no more than 2. So the result would be 1, 2, because each of these takes up more than a third of the array. But it can't really be larger than that. And it could theoretically be 0. Like if we have an array like 1, 2, 3, 4, none of these take up more than a third of the array. So in that case, the output is going to be 0. We're not guaranteed anything in this problem. So those are a couple points I wanted to make, but going back to the hash map solution. Yes, a hash map is actually perfectly valid. What is going to be the time complexity for that? Probably O of n to count all of the occurrences, and also O of n for the size of the hash map in the worst case. That works, but we are actually able to take the space and reduce it down to big O of 1. That's actually the follow-up question if you go to the bottom of the description of this question. And it's possible, but it's not necessarily easy, or at least easy to come up with. Once you know it, it's actually pretty easy. The concept is pretty simple. We once again actually use a hash map, but this time we're going to make sure the size of the hash map is always going to be less than 3. In other words, the idea here is going to be that this hash map only contains the 2 most frequent elements. So the idea is actually simple enough. Now, coming up with it and implementing it is not simple until you actually see it. And to show you, I'm going to basically go through an example. So let's do that now. So suppose we have an array like this. This is our hash map. We're mapping a number to the count of that number. So we start here. We have a 1. We add 1 to the hash map. What's the count of it? It's of course 1. Then we have a 2. So these are our 2 most frequent elements so far. Each has a count of 1. Now we get the third element, 3. So we map it to its count 3. But we don't want this guy to grow arbitrarily large, so we have to restrict it. So what do? I mean, all 3 of these have the exact same length. Which one do we remove? We can't pick. I mean, there's no intelligent way to pick which one to remove. But what if I told you we can remove all of them? But why? Why can we remove all of them? I thought we're trying to count the 2 most frequent elements. Well, yes, we are trying to do that, but we also know that we don't really care about any of the candidates if the count of those candidates is less than a third or even equal to a third of the input. It has to be greater than the length, or it has to be greater than a third of the length of the input. So my argument to you is this: as soon as the length of the hash map becomes greater than 2, meaning basically 3, once it's equal to 3, we are going to then decrement the count of every single number in the input. And if the count of any of the elements is equal to 0, we remove that from the hash map. So this time we're removing all 3, but it's guaranteed that we would always remove at least one of them. And that's because at some point, let's say the count was 2 of each of these, and then we add a 3, and then the count is 1. When we add the third element, the count is always going to be 1. So at the very least, we're always going to remove at least one element to make sure that the size of the hash map does not become greater than 2. That's kind of the intuition here. So now just going through the rest of this example, let's say our now hash map is empty. We've already gone through these 3 elements. Now we get a 1, we add it back to the hash map, count is 1. Now we get a 2, add it back to the hash map, count is 1. So what do we return in this case? We return these 2 elements. They're the 2 most frequent elements. But in this case, it does work out. The length of this is 5. Divide that by 3 and round down, you get 1. Each of these has a count of 2. So obviously, this has a count, a frequency greater than this, and this also has a frequency greater than that. But that's not always going to be the case, actually. If we had a different input array 1, 2, 3, 4, 5, 6, and then a 7 and 8, actually, we would get kind of the same thing. First, we'd add these 3 to the hash map and then remove all 3 of them. Then we'd add these 3 to the hash map and then once again remove all of them. By the end, these 2 elements, 7 and 8, would be left in the hash map, and we don't want to return those as a result. They are definitely not taking up more than a third of the array. So what we learned here is that even though we are theoretically trying to keep the two most frequent elements in this hash map, that's not actually what we're doing. We actually don't end up with the two most frequent elements, at least not in this example, because all of these are the most frequent. They all have the same frequency. And just because these two are left in the hash map doesn't mean they take up more than a third of the array. So what we have to do when we have this resulting hash map, we then have to verify for each number, is the count actually greater than a third of the length? And that's not difficult to do. We can literally just get the real count of 7 and 8, which is actually the same. It's going to be 1 for each of them, and then compare that to n divided by 3. So we can verify that these are actually taking up more than a third of the array. Another quick example to really get this point across is, what if the array actually looked like this? We have a 1, 2, 1, 2, 1, 2, and then we start getting some different elements like 3, 4, 5. Well, our hash map would eventually, like by the time we get to this point, our hash map would map 1 to 3, would map 2 also to 3, and then we'd insert a 3. We'd get 3 maps to 1. And at this point, we'd decrement each of these by 1, which would end up removing this, and we'd get these two set to 2 each. Once again, when we get to the 4, we're going to do the same thing, add 4 to the hash map, and then remove it because our length of the hash map became 3, so we have to decrement each of these by 1, so then we decrement this and this down to 1 as well, and then lastly, we'd get to 5. Now, 5 is going to map to 1. I know this drawing is getting a bit bad, but we'd remove 5. We'd take this count, decrement it to 0, take this count, and also decrement it to 0. And now these would be popped. And by the end, we'd have an empty hash map. Basically, there's no solution to this problem. Does that look right to you? Yeah, because 1 takes up exactly a third of the array, 2 takes up a third of the array, and here is also a third of the array. But we want elements that take up more than a third of the array. So if we instead, in this example, actually didn't have a 5, then by the end of inserting this and this, we'd have a count of 1 for each of these. That doesn't guarantee a solution, but then we would verify that the counts, the true counts of 1 and 2, which are 3, is going to be greater than 8 divided by 3, rounding down, which is going to be 2. So this actually does work. I know it's not easy to come up with, and that's because it's a hard problem, especially if you're trying to solve this problem like this with constant memory, but that's kind of the benefit. But now let's go ahead and code it up. So the first thing I'm going to do is create a hash map, and in Python you can actually create default dictionaries, which means you can have a default value. In this case, I'm passing an int, which means the default is going to be an integer of 0. So now when we go through every number in here and try to count it, and we try to increment the count of this by 1, we don't have to verify that n is already in the hash map, because if it's not, this will give it a default value of 0, and then we'll increment 0 to 1. But we have this is fine. We're just getting the count of each number. But remember, if the length of the hash map is greater than 2, then we got to do some stuff. We have to decrement the count by 1. Now, I know that this is going to get highly nested, so I'm actually going to do the opposite here. I'm going to say if the count is less than or equal to 2, let's continue, meaning we don't have to decrement the count. We just continue to the next iteration of the loop. But if it is actually greater than 2, then we have to go through every number and count, and I'm going to do that like this, count.items in the hash map. It just is kind of a shorthand. And then we unpack the key, which is the number, and the count, and we're going to check. And one way to do this would be to just take count of n and decrement it by 1. And then after here, we could then go through the count hash map again. And if any of the counts are equal to 0, we remove them. You might think first to try that in here, put an if statement here. If the count of n now is equal to 0, can't we just do count.popn? No, because we're iterating over a hash map and we don't want to change the length of the hash map as we iterate over it. So this is not a good thing to do. So another way of writing this, there is that two loop solution I talked about, but another way is to actually declare a new items in the hash map. here. I'm going to say don't have to, then we have to go through every number and count, and I'm going to do that like this, count.items in the hash map. It just is kind of a shorthand. And then we unpack the key, which is the number, and the count, and we're going to check. And one way to do this would be to just take count of n and decrement it by 1. And then after here, we could then go through the count hash map again. And if any of the counts are equal to 0, we remove them. You might think first to try that in here, like put an if statement here. If the count of n now is equal to 0, can't we just do count.popn? No, because we're iterating over a hash map and we don't want to change the length of the hash map as we iterate over it. So this is not a good thing to do. So another way of writing this, there is that like 2 loop solution I talked about, but another way is to actually declare a new hash map, a new counter, and I'm going to do the same thing, default dict with int, and doing it this way, we can check if the count is greater than 1, then we know that this number is going to go in the new hash map. Why did I do that? And what is the count going to be? The count is going to be the original count minus 1. That probably makes sense. It's same as the drawing explanation, but why am I only adding elements that have a count of greater than 1 to the new count hash map? Well, because if it had a count of 1, that would mean we're decrementing it down to 0. And of course, we don't want to keep anything that has a count of 0 in the hash map. So that's why I'm writing it this way. Now, after we do that, we want to update the count to the new count hash map, and then we're done. After we do this, if there is a solution to this problem, like if any elements in the array show up greater than a third of the time, they will be in this count hash map. This is actually not necessarily going to be the 2 most frequent elements, as we talked about earlier. But if there's a solution, we know for sure that those elements will be in there, and we want to add them to an array before we return them. And how do we verify that those elements do show up greater than a third of the time? Well, it's pretty easy. Just iterate over those elements. And this is misleading. Like this is not going to be big O of n time. We know there's at most 2 elements in that hash map. Now we want to check, well, what's the count of each element? And this time I'm going to do something not the most efficient, but it's easy to code. And I don't think it's bad. It's not going to affect the overall time complexity. I'm just going to take nums.count of n. This is a linear time operation. But as I talked about, this is only going to execute 2 times, at most 2 times. So doing a linear time operation 2 times is not that bad. It doesn't affect the overall time complexity. It's still a linear time solution. But we're checking the count of this, and we just want to make sure it's greater than the length of nums divided by 3. If it is, then we will append it to the result. That's the entire code. Now let's run it to make sure that it works. And as you can see on the left, yes, it does, and it's pretty efficient. If you found this helpful, please like and subscribe. If you're preparing for coding interviews, check out LeetCode.io. Thanks for watching, and I'll see you soon.
We got the solution. So that's that. The 323, let's take this as an example. 32315. 32315573535. So here the solution here is take a hash map of 3 size. Let's take a hash map of size 3. So first 3 is count 1, next 2 is count 1, next 3 is again count 2, next 1 is count 1. So once it's full, decrement the value by 1. So this will become 3, 2, 3. No, sorry, 3, 2, 1. This will become 1. This will become 0. This 1 will become 0. Remove this 2. We were here. Now let's continue. 5. So 5 instead of this, you'll get 5 here. So 5 will be 1. Again 5 will be 2. Next 7 will be 1. Now again 3 elements are there. Now decrement is the 1. And rewrite this here. So 3 of 0, 5 of 1, 7 of 0. Remove this both. Now we are left with this. We're here. Now it's 3 again 3. So 3 of 1. Next 5 of 2. Next 3 of 2. Next 7 of 1. We are end with array. Once we reach 3, now we are end. This is fine. Now we reach 3. Now decrement everything over 5 1 3 1 7 0. So we have 3 and 5. So 3 and 5 will be the output. So we get so greater, right? 5 will become 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 by 3. 3 is the 9. 1, 2, 3. 3, 2. It will become 1. Now 3 will become 0. I will become 2. I will become 1. This will become 5. Will become 2. We have 7, 1 of them. 1, 2, 3. Okay, let's do it again. 3, 2, 3, 1, 5, 5, 7. 3, 2, 3, 1, 3, 2, 3, 1, 5, 5, 7, 3, 5, 3, 7. 5, 3, 7. So 3 will become 2 will become 1, 3 will become 2, 1 will become 1. We are done. We are here. Now this will become 3 will become 1, 2 will become 0, 1 will become 0, 3 1 next, 5 will be 2, 7 will be 1. Now this will become 3 will become 0, 5 will become 1, 7 will become 0. So this will become 5 is to 1. Okay. So this is again. Now we are here. Again. 3 will become 1, 5 will become 2, 3 will also become 2, become 1. Now minus it. This will become the 5 and 3 are supposed to be answers. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So 11 by 3. 3 should be greater than 3. Is 3 greater than 3? 1, 2, 3, 4. Yeah. But 5 is coming 3. 5 should not be coming. How is this working? Hmm. Okay, let's try to put it up. Take, uh, is it correct? Is that like default? So we took the default now for element 10. No, hmm, we have to add in. So size, syntax, yeah, arithmetic dictionary size. I need some syntax. Len. Okay, then. Rejected in C++. Mistakes. Greater than 2. So we can even do inverse. Um, yeah. No, we'll do the normal. Greater than 2 is greater than 2. So key comma and pick dot uh, that's elements pick dot items. So this is for only syntax. Yeah, I'm doing on it. Dot items. The key and how really the key is let's take the flag Not flat also. Oh, target. Target is equal to n. How did he extract it?
That bad. It doesn't. But as I talked about, this is only going to execute 2 times, at most 2 times. As I talked about, this is only going to execute 2 times, at most 2 times. But as I talked about, this count of n, this is not going to affect the overall time complexity,
And then
but
count.
it's easy to code, and I'm going to do something not the most efficient, but it's easy to code, and I don't think it's bad. It's not going to affect the overall time complexity. I'm just going to take nums dot count of n. This is a linear time operation, but as I talked about, this is only going to execute 2 times, at most 2 times. So doing a linear time operation 2 times is not that bad. It doesn't affect the overall time complexity. It's still a linear time solution, but we're checking the count of this, and we just want to make sure it's greater than the length
target.
of nums divided by 3. If
3.
it is, then we will append it to the result. That's the entire code.
This. At last condition, it is being checked. So let's submit it. I think should be done. Oh my god, I guess they're getting TLE. It's taking time. So, yeah. So time limit exceed 94. Last test case. We failed in the last test case. We have to remove the dictionary.
Now let's run it to make sure that it works. And as you can see on the
So spreading a new dictionary. Okay. Hmm. So I think that's better to create a new dictionary. Try it again. TLE, come on, man. Hmm. Okay. That's what he mentioned in the video, right? Same error again. Or you get same error. Okay. Let us say earlier. Yeah, I think we are done. Which 5% is too bad actually. Let's optimize it, I think, because of this. So instead of us actually iterating, popping, doing all these things, we can reassign it to a new dictionary. So actually, let's take, yeah, let's try removing this scrap. Let's remove this scrap out. Oh my god, no, no, no. I submitted it by mistake, it's fine. If length of dictionary is 2, okay, new dict if DSCPT dict of k less than 0, is greater than 0. Will this work? That's how I initialized it.
That those elements will be in there, and we want to add them to an array before we return them. And how do we verify that?
Why the default deck? Okay, sorry. My bad. The start of range, I don't think so. No, it should be faster. Okay, just the same. Maybe it in memory actually. Yeah, I think this is it. Don't want to waste more time. Let's Write down the approach here. And one shift all of these. With real ones now. So, yeah. So yeah, we use this. Okay, we're done. Let's change this thing. We solved one. We almost took an hour, but it's okay. Let's continue the system. Now, some of are very equal to k. I think I tried this system. Stream is running. Yeah, I'm doing too slow. Let's speed it up. Integer nums and integer k. K. Non-empty sequence of element with uh, I tried solving this, but I don't know, I couldn't solve it. Almost got it. Okay, okay, okay. Let's not waste time. Let's try to think again. I don't know when did I solve it though. I guess 2, 3 days back. Okay, I did not submit, so I did not get the answer. So we are given an integer nums and return the total number of subarrays with sum equals k. Total number of subarrays with sum equals k. So this is 160. Subarray sum equals k. Okay. Okay. Number of subarrays whose sum equals k. So let's start here. The sum equals k. So 1. The sum equals k 1. And it's 2. Okay. 1, 2, 3. So it cannot repeat. 1, 2, 3. So 1, 2, 3. K is equal to 3. So 1 plus 2 is 3. Again 3. So this will become 2. This will become 2. This will just 2. Yes. So I got a problem. How to solve this? Okay. Yes. Is there any constraints? Okay. K can be. Okay. Fine. These are fine. 32-bit constraints. Fine. Fine. Let's take an example. 1, 2, 3, 4, 5, 6. And let's take 5. So it should be continuous. So I'll take this here and I'll take here 1 plus 2, 3. Let's take prefix on, I guess. Let's try. So we'll try to 30. If you're not able to see the solution. So 1 prefix sum 1, then 3, then 6, then 10, then 15, then 21. Prefix sum. If I take if I take reverse prefix sum 6, 11, 15, 18, 20, 21. This is reverse prefix sum. So we check anyone's sum is 5. No, no 5. Fine. Now we check anyone's difference is 5. Yeah, this is 5. 6. This is again 5. So let's take 1, 3, 6, 10, 15, 21. This is the prefix sum. Now we know that we need k is equal to 5. So let's take this as I, let's take this as j. So A of areas I is equal to array. A of J minus A of I should be equal to K. Okay. Or A of I equals K minus A of J. Is also fine. K minus A of J. Hmm. So let's store this in hash map. Not that I think. K minus A of J. What is K minus A of J? 6. So 21 minus 15. 21 minus 15, 6. 21. Can I take 21 minus 15? 6. Okay. 21 minus 10. 21 minus 10. 11. 21 minus 6. 15. 16, I guess. 16. Or 15, sorry. 15. 16, 17, 89, 20, 15. 21 minus 6. So 15. 21 minus 3. 18. 17. 20. 21 minus 1. 20. Same way. Now. 15 minus 10. 5. 15 minus 6. Don't know. 9. 15 minus 3. 12. So we got 1 as 5. Carry on. 10 minus 6. 4. 10 minus 3. 7. 10 minus 1. 2. Okay. Now 6 minus 3. 3. Okay. Okay. I don't think we'll get again. 6 minus 3. 3. 6 minus 1 is 5. We get 5 here. So 2 we are getting 5. So we can use this approach. So first we find the prefix sums. Then we store first find prefix sum. Prefix sum in free array. Now use two pointer to iterate to free array and find the key of a minus 3 of I and store it in Atma. And then yeah, then just hash up and then just get value hash of key will be equal to count. So we can actually we can eliminate this We can eliminate this hash map by just maintaining a counter and checking if it is equal to 5. So that is better, I think. Let's do this. Let's reset this. So I had idea about this problem, so that's the reason I was able to derive the solution. I think I've seen the solution, but yeah, I nothing like yeah. So that I felt pretty easy. I mean, not pretty easy, but still, it was kind of hard. Let's see what my stream. But yeah, I nothing like yeah. So that I felt pretty easy. I mean, not pretty easy, but still, it was kind of hard. Let's see what my stream. But yeah, I nothing like yeah. So that I felt pretty easy. I mean, not no, it's not so pretty. 0 into size of num size. Okay, now uh, even 10 none. So it's in range and because I'm listening. And then we can say yeah, this is just debug. And then to so yeah, you see this was a bug. So yeah, okay, it's working. So 0 1 2 0 1 2 3, yes, correct. So we got the prefix array. Now hmm, 2 and 2 is equal to uh, I have to do it reverse, right? Um, minus 0. Next one, it should go to 0. Let's actually use some copilot here. Okay, you have to mention -1. Okay. 4 and 20 -1 -1. E1 -1 comma -1. So if is equal to right. This should work. Why doesn't it work? 1, 2, 3, I think, because of the unique. Okay. So 1, 3, 6. We need distance of 3, right? 3, 2. Yeah, I think that was that one. Small entry. Okay. 2 to 0. Reverse P2 is equal to P1 minus 1. Range P1. Okay, I got the mistake. Incorrect. While P2 is greater than minus 1. This should work. Okay. 2 4 1 1 1. 2, right? This 1 2 3. 3 minus 2 1 no? 3 minus 1 2. Yes. No. 2 minus 1. So prefix sum is 2. Okay. If prefix sum is also 2, we have to increase the count. Or this should do the job. Okay. For 1 to 3. 3 is 1. Correct. It's 2. We got 2. But going one more. 3. Okay, I think we'll remove this n. Prefix sums. That should cover it up. This is fine. Here, if you write pre also, it's just the same. So if I submit, hope I don't get really. I think, yeah, really, it's passed. How to optimize it? The approach is okay. It's correct. Optimization issues. The two pointer is giving DL. Mm, let's see. But yeah, we did get the approach. That's correct. Mostly DLE. So let's see how he solves it. I think ours is brute force. Okay, we have to solve using hash map. Prefix sum. We're almost there. Let's see.
Hey everyone, welcome back, and let's write some more neat code today. So today let's solve subarray sum equals k. So simply we are given an array of integers nums, and we are given a target integer k, and we want to return the total number of contiguous subarrays which sum up to the value k. This is our target value. So how many continuous subarrays sum up to 2? Well, we have one subarray with the first 2 elements, and then we have a second subarray with the last 2 elements. That's 2. How many different subarrays sum up to target value 3? Well, we have one subarray from the beginning, and then we have another subarray at the end. Now let's think about the brute force approach first. That's going to be n squared. Why is it going to be n squared? Because we have n squared different subarrays inside of the array. So if we just check every single subarray, right, we start here. Is this sum up to the target k? Nope. Okay, does this sum up to the target k? Yes, it does. Then we check the entire thing. Does this
That's
sum up
what
to the
we were
target k?
doing.
Nope, it doesn't. And then we can start over here. Does this sum up to the target? Nope. Does this sum up to the target? Yes. And then we can go here. Does this sum up to the target? No, it does not. And then we're done, right? So we checked every single subarray. That's n squared time. And then your next thought might be, okay, n squared, maybe we can improve that. Maybe we can use 2 pointers. Maybe we can even do a sliding window. So for example, this is our first subarray, right? It's too small, so we add values. This is our next subarray. It's the perfect size. This is our next subarray, and this is too big. So what would we want to do then? Well, maybe we could try, taking the left part and moving it, right? Moving our left pointer here because we want to decrease the size or the total sum of the window. After you read the constraints, you'll know that that's not possible. The reason why is because the values in nums could be negative. So just by adding a value to our subarray, like adding another value, doesn't guarantee we're increasing the size, and removing a value doesn't guarantee that we're decreasing the size because some of the values could be negative. Now, it still is possible to improve the brute force solution into a linear time solution, and it's not super intuitive, but you can use the brute force solution as some intuition to get to the better solution. So that's kind of what I'm going to try to explain, and then once you know it, the code is actually pretty easy to write. So let's kind of go through that intuition now. So yes, we are going to be using a hash map in this problem where the key value is going to be the prefix sum, and the value of the hash map is going to be the count of how many times that particular prefix sum occurs. But let me actually run through why that's going to work for us. So we see that the target value is k, so let's try out the brute force approach. So we're going to first start at this subarray, right? Just one value. Our sum so far is 1. Then we're going to do the first 2 values. The sum so far is 2. Then we're going to add a third value. Now the sum so far is 3, right? So we found one subarray, right? We can kind of keep track of that. We have one subarray so far. Next, we are going to go to this part, the fourth element, right? Now our sum is 4. And of course, we're going to do the same thing for the remainder, right? This is going to be 5. This is going to be 6, etc. But let's just notice a tiny bit of repeated work we're doing. Next, I'm going to start over here at the second element, right? Brute force it from here. So far we have 1. Now we have 2. We added a second element. And now we added a third element. So yes, now we reached the target, right? This is sum k. So we can add another one to our total, the number of subarrays we found with k, right? The first one was these 3 elements. The next one is these 3 elements. But notice how we computed this entire sum, right? When we're computing these 3 values, we're basically doing a ton of repeated work that we just did, right? So how could we have gotten this 3 sum a little bit quicker, right? These 3 values summed together a little bit quicker. Well, when we were over here, right, when we had iterated through these first 4 elements, we could have just said, okay, take the entire sum minus the first prefix, right? Just the first value minus that. That would have given us 3, right? But if we're trying to compute every single subarray, right, because we know the next go around when we iterate through the loop, we're going to be starting at this value, right? And then eventually we're going to get to a subarray like this. So when we were going through it the first time with this blue portion, we could have gotten this pretty easily as well. We could have just taken the entire sum minus the first 2 values, which is a prefix of the array, right? But that's also brute force, right? We're not doing anything better. All we're doing is still creating every single subarray. So is there some intuition we can use? Can we somehow be a little bit greedier? Notice how when we've gotten this subarray, our sum so far is equal to 4, right? So what we're looking for, in other words, is can we chop off some prefix of this array, of this entire array? Can we chop off a prefix such that we can make this sum match k? The answer is yes, because we can calculate it, right? Our sum is 4, so let's get sum minus k, which is going to be 4 minus 3, which is 1, right? So we know that so far the entire sum is 4. If we can chop off a prefix of 1, we will still have a contiguous subarray, right, that will exactly match k. Now the only question is, does there exist a prefix in this subarray, right? Not in the entire array. Does there exist a prefix in this portion starting at the beginning that we can remove? Because remember, we want a contiguous subarray. Can we chop off a prefix that has an exact value of 1? Well, we can if we maintain a count of it, right? If every time we compute a prefix, if we add it to our hash map and count how many prefixes have a value of 1. And the reason we're counting is because, remember, since we could have possibly negative values, like this could have been a negative one, there could be multiple prefixes that have a prefix of 1. Because, you know, this is one prefix that sums up to 1. This is another prefix that sums up to 1, right? Because we have a negative one in the middle. So that's why we have to count the numbers. But also, one thing, we can't just go on and compute every prefix before we actually start building up our result. We have to do it simultaneously, right? Because if we just compute every single prefix, then when we get, when we're at this point, right, we're trying to get, okay, how many prefixes have just a sum of 1? Well, if we have gotten every single prefix already, then that'll have been added to our hash map. We might end up removing a prefix like this, right? We can't do that. We're not allowed to do that. When we're at this portion, we only want to remove prefixes that are a subarray of this, right? And of course, we don't want to remove the entire array because it's possible our k value could actually be 0, in which case we don't want we don't want to take this and say, okay, remove the entire thing. That sums up to 0. And there's one last edge case we have to worry about. So let's say our k is 3, right? Once we've gotten to this point, our sum is 3, right? So we're going to take 3 minus 3, which is equal to 0, right? At this point, we don't have any prefixes with a sum of 0. So what we're going to say is, okay, since no prefix has a sum of 0, right, then we're not going to end up updating our result. But we don't want to do that. So as a base case, what we're going to say is to our prefix sum, we're going to add a 0 value and say that the count is 1. Basically, we're saying there is a prefix, the empty prefix that has a sum of 0. So now let me walk you through the algorithm. It's going to be a linear time algorithm. I'm going to change this to a -1 just to make the problem a little bit more interesting. So we're going to start at the beginning, add every single value that we can to our array on each iteration, add that to the sum, and every time we compute a prefix, after we are done updating our result potentially, that's when we're going to go ahead and add that prefix to the prefix map. So we start at the first value, we get a sum of 1, 1 minus 3 is -2. Does -2 exist in our prefix map? Nope, it does not. So we continue, but before we continue, we're going to take this prefix that we just computed, 1, and add it to our prefix map. So prefix of 1 has a count of 1 so far. Next, we are going to get the next value. So now we have a sum of 0. 0 minus 3 is -3. Do we have a -3 in our prefix map that we can potentially remove from this array that would give us the total sum of the array as being the target? Nope, we do not. So we continue, but before we continue, we see, okay, we computed a prefix of sum 0. So let's increment the count of prefix of sum 0. So this is now going to be a 2. And now we're going to add the third element to our sum. So now we're going to have a sum of +1. So we're going to take 1 minus the k value 3, -2. Does a -2 exist in our prefix map? Nope, it does not. But we can say that, okay, we computed a sum of 1 again, right? So now we can take the prefix sum of 1 and say that there's 2 different prefixes, this one and this one, that sum up to 1. And we're just going to continue. So at the next iteration, now we have a sum of 2. 2 minus k is going to be -1. Do we have a -1 in our prefix? Not just yet. So let's continue. And now we add the fifth element. So now we have a sum of 3, right? So we're going to take 3 minus k, which is also 3, right? And we're going to get 0. Do we have a prefix sum of 0? Finally, we do. So what are we going to do? We're going to take the count, the number of prefixes that we had that summed to 0 and say, okay, there's 2 different ways that we can create a subarray of k. So we're going to take our result, which is initially 0, increment it by 2. But hold on, what did we just do? Let's think about it for a second. We said, okay, the entire sum of this subarray is equal to 3. And we said, okay, 3 minus k is 0. That means we need to remove a 0-sum subarray from this subarray to get us to the target value, right? So one subarray is, okay, if we remove, an empty subarray, right? Why does that work? Because take a look. This is a subarray that sums up to 3, right? That's the obvious one. So that's where our 2 comes from, right? So far we have one of the 2 ways, but let's continue. There's another subarray, this subarray, right, that has a sum of 0. So if we remove this subarray from our original subarray, then we're removing 0 from the subarray, so this sum stays as 0. So this is the second subarray that sums up to 3 that we have found that ends at this position. So great, so our result so far is 2, and don't forget this subarray had a sum of 3, so let's say one prefix has a sum of 3 so far. And next, we're finally at the last iteration of the loop. So now our sum is 4. 4 minus k, which is 3, is going to be +1. So how many prefix sums do we have with sum of +1? We have 2, so that means we're going to add 2 to our result. Because what we're saying is, ending at this position, how many subarrays could we get that sum up to 3? Well, because the total sum of this is 4, and we know that we have 2 prefix sums that start here that sum up to 1, we can remove 2 different prefixes that will make this equal to 3. We can remove this prefix, right? That's one prefix that sums up to 1. And then when you look at this sums up to the target 3. We can remove another prefix sum. Remember, this also sums up to 1. If we remove this, then we also have a subarray that sums up to 3. So we have two different subarrays that end at this position that sum up to the target 3. And once we've done that, we've iterated through the entire array once, we're done, right? We did an exhaustive approach. So we ended up getting a result of 4. There's 4 different subarrays in this entire thing that can sum up to 3. So obviously, it's a linear time solution as well as linear memory because we're using this hash map. But that being said, now we can jump into the code, and the code is pretty easy once the entire array.
Basically, he's taking an array, is just calculating the sum for every, like in a linear part from first to end, if n is maintaining a hash map. If that, okay, you got a sum of 1. So if it's existing in that map, if it's not, just is adding it. So, okay. So how many 1 exists? If I remove it, it will become 0. Okay, so if there are 2, it will become 2. Okay, got it, got it.
Of 4, there's 4 different subarrays in this entire thing that can sum up to 3. So obviously, it's a linear time solution as well as linear memory because we're using this hash map. But that being said, now we can jump into the code, and the code is pretty easy once you can figure this out. So we are going to have a result variable, which initially is going to be 0. We're also going to maintain the current sum, which is initially going to be 0 as well. And we're also going to have a hash map, let's call it prefix sums, and it's not going to initially be empty. Remember, we have a base case of 0. We have a single prefix sum that sums up to 0. So that's what we're going to say, like, the empty subarray. And then we're going to go through every single value in the input array, add it to the current sum, right? We want to know what the current sum is. And then we want to know what's the difference that we're looking for. The difference is current sum minus k, because we know if we can remove a prefix sum of size diff, then we can find a potential result. And we could have multiple prefix sums that sum up to diff. So we want to take that and add it to the result. So we're going to say result dot add to it whatever prefix dot get sum up to diff. Now it's possible that this diff does not exist in prefix sums, and in Python you can return a default value of 0 if this diff does not exist in prefix sums. And then after we do that, that's when we want to add to prefix sums the current sum that we just computed. So prefix sums at position diff, or the key value diff, we want to say 1 plus whatever it already is. So let's copy and paste this. Oh, and it's actually not diff. We're computing the current sum, right? That's what our prefix sum is right now, current sum. And this also can be changed to current sum. So with this line, all we're doing is just incrementing the number of prefix sums that have this particular sum value. And believe it or not, this is the entire solution, right? We only have to iterate through the entire array once, maintaining some hash map. And as you can see, the solution is pretty efficient. So I hope that this was helpful. It's not a very easy problem, even though the code is pretty short and easy. So I hope this was helpful.
Okay. This is also taking an hour. Okay, let's get solving this now. So what we tried was again a brute force approach. So optimal approach. Optimal approach is pretty simple. So we just so let's take one more. 3. So now take this. Now this is dictionary. 0 is equal to 1. This is default. Now 1. Prefix sum is equal to 1. Now
We have two different subarrays that end at this position that sum up to the target 3. And once we've done that, we've iterated through the entire array once. We're done, right?
okay. Let's code it up. So this we did give it a nice try. Let's take count is equal to 0. Depth is equal to this. Right. With default value 0 to 1. That's the problem. Where I free sum 0 where I nums free sum as I is equal to k free sum def But the we are storing three sum.
Or minus k, which is 3, is going to be positive 1. So how many prefix sums do we have with sum of positive 1? We have 2, so that means we're going to add 2 to our result. Because what we're saying is ending at this position, how many we have subarray remove 0. So
Get this comma 0. So let's take A is equal to with A is equal to take dot get def of 0. Of 0. Okay, now take def of 3 sum. Sum comma 0 plus 1. Return the shape here for I in nums. 3 sum is equal to 3 sum plus I. The difference is equal to K. No, it's 3 sum minus K. 3 sum minus K, I think. Okay, correct. So difference should be equal to minus K. So whatever is left out, if it's there, no? I mean, this is hard. How can anybody think of this as a solution? Here the concept is subarray. So you're storing sum of subarrays and difference of K. Yes, having reached towards 2%, we're going to slow. Now it's time for the third one. We'll see that at last. Now 82 were done. So we'll finish that. Hmm. So LeetCode. Let's we'll look at it. I think 84 or something. So we'll keep it like that. We can change it. Shoes? No, it's fine. It's fine. Okay. Just- Now we are in the last question. First missing positive. And, and I think this will be easy. Missing positive. Sorry, what is this question? I Yeah, I think I solved this. Yeah, I've solved this, but not in this. Yeah. I've done this now, so there is nothing. So O of one, O of n, O of one. So my solution beats 5%. So you can see everyone else solved it. So mine is has a brute force approach or something. But let's see. So um, I, negative, so let's take 3, 4, minus 1. Let's take 1, 2, 0. Let's try solving it. What D1? Hmm. Prefix sum 1, 3, 3. 3 minus 3, 0. 3 minus 1, 2, 1. 1 minus 0. First element 1. Hmm. Take the highest. 7, 8, 9, 11, 12. Take the highest. Linear space. Huh? Auxiliary space. Okay. Can't use hash map. We can just sort it. Okay. Brute force is pretty easy. Boolean array. Sorting, I think, is already this way. Negative marking. Cycle sort. Negative marking. Let's read a negative marking.
Hey everyone, welcome back, and let's write some more neat code today. So today let's solve first missing positive. This is a hard problem, not because it's hard to solve. There's a variety of solutions. One solution is an n log n solution. Another solution is a linear time solution, but that one takes also linear time memory as well. So time and memory, but there's also a solution with linear time, but it takes constant memory, and that's the difficult solution to create, which is why this problem is categorized as hard. That's the one I'm going to be mostly going over today. So we're given an unsorted integer array of nums. Simply, we just want to find the smallest missing positive integer. What does that mean? Well, my question is, what's the smallest positive integer in general? What's the smallest positive integer?
Yeah.
1, right? That's pretty simple. We know that 1 is the smallest positive integer. The second smallest is 2. The third smallest is 3. So we want to know, given an input array of nums, it's not sorted necessarily, but we want to know what's the smallest. So initially we're going to say, without even looking at the array, we're going to say, well, the smallest possible could be 1, right? So let's iterate through the array now. First value 1. So okay, the solution is not going to be 1. Maybe it's going to be 2, right? Let's go to the next value. Oops, there's a 2 here, right? So next smallest possible could be 3. We go to the next value, it's a 0, right? That's not a positive integer, so we don't care, right? And it's definitely not a 3, so we don't care. So now we've run out of the array. What's the smallest missing positive integer? 3, right? We were keeping track of that, so we're going to return 3. So basically the way I was going through the problem right now is one way you could solve it. But to solve it in that way, you would need to sort the input array in ascending order. So we're going to sort of be greedy here, right? We're just going to say 1 is the smallest positive integer that's missing, right? And since we know our input array is sorted, we know that if there exists a 1, then clearly we were wrong in our assumption, right? So in this case, we do see a 1, so we were wrong. So then we'll change what our solution is to a 2, right? And then we'll see a 2, and then we know we were wrong again, right? So then we're going to change our answer to a 3. We're going to say, okay, maybe 3 is the smallest missing positive integer, and then we're going to get to a 4, right? And so once we've gotten to a 4, we know every value that's going to come after it is going to be greater than or equal to 3. So at that point, we basically know, yes, 3 was the one that was the smallest missing positive integer. Now, the time complexity is going to be n log n because we are sorting this input array. But one thing to notice with this is see the size of our input array. The size of the input array is 3, right? So that means in the worst case, the smallest missing positive integer in the worst case, right? In the largest it could possibly be is going to be 4. Why is that? Why is it going to be 4 in the worst case? Well, take a look at this. What if the input array we got was 1, 2, 3, right? Remember, the size of our input array is limited to size 3. So in this case, if we had 1, 2, 3, then we know that n would be 4. The result would be 4 because we're missing, the smallest positive integer we're missing is the 4 that would go here, right? If
Yes, that's it. Step on 5.
Hello.
Smooth.
Or in the worst case? Well, take a look at this. What if the input array we got was 1, 2, 3, right? Remember, the size of our input array is limited to size 3. So in this case, if we had 1, 2, 3, then we know that n would be 4. The result would be 4 because we're missing, the smallest positive integer we're missing is the 4 that would go here, right? If, for example, we did not have all 3 of these, right? Maybe we're missing that 3 like we had previously, then we would have the n equals 3, right? Or, for example, maybe we would be missing a 2, right? Maybe we have 1, 2, 3, 4. Then in that case, we'd have a 2 that goes here, right? 2, 3, 4. Then in that case, the smallest missing is going to be 1. But basically, no matter how you arrange this, right? Maybe we would just have really big integers. For example, 10, 11, 12. What's the smallest missing in that case? Again, that's just going to be n equals 1, right? So basically what I'm saying here is no matter what our input array is, no matter what the values go in it, the answer, our result, n, the smallest missing positive integer, is going to belong to the set between 1 and length of the array plus 1. That's pretty obvious, right? That's mathematically obvious, right? We could not have a smallest missing positive integer that would be larger than this if our input array is just, limited in size. We could not have a missing positive integer. So this is our solution set, right? And we're given that based on the length of the input array. So in reality, we actually don't need to sort this input array. We can actually take the input array, convert it into a hash set. Why are we converting it into a hash set? Because we're going to brute force this. We're going to go through every single value from 1 to n plus 1, right? Or the length of the array plus 1. So we know the solution belongs to this. We're just going to have a for loop that goes through all of these values, tries each of them, right? So for example, we're going to try n equals 1. We're going to check, does n equals 1 exist inside of our hash set? And we can check that in O of 1 time, right? If it does exist in our hash set, then we're going to try n equals 2. Right? If that exists, then we're going to try the next number, right? N equals 3, so on and so on. If n equals 3, for example, does not exist inside of our hash set, then we're going to return n equals 3 as our result, the smallest missing positive integer. If, for example, we go through the entire loop and we don't find any value, so for example, if we tried the n equals the length of the array, and even that was found in the hash set, then by default, we're going to return n equals the length of the array plus 1, right? This is our worst case scenario. This is the largest it could possibly be. And so since each of these operations just takes O of 1 time, and we're doing it for every value based on the length of the input array, this is going to be 1 times n. That's just big O of n time complexity. But the hash set is taking extra memory, right? So that's going to be big O of n memory as well. But we can use this to our advantage. We can devise a way where we actually don't need a hash set. How can we do that? Well, we are going to need some extra memory, but it turns out we can use this input array as that extra memory, so it doesn't actually count as extra memory. So we can take this time complexity, or this memory complexity, big O of n, and reduce it all the way down to big O of 1 by using the input array as our extra memory. So like I said, we're going to be using the input array as extra memory. Just like we used an extra memory hash set, we're going to basically be using our input array as a hash set. How am I going to do that? Remember how our solution set is basically from 1 all the way to the length of the array plus 1, right? This is our solution set between 1 and the length of the array plus 1. So for every value between 1 and the length of the array, right, we have an index for that, right? So 1 is going to be mapped to the 0th index, right? 0 index, 1 index, 2 index, 3 index, right? The last value, length of the entire input array, is going to be mapped to length of the array minus 1 index, right? So in this case, we can see the length of the input array is 4. So 4 minus 1 is going to take us to this index, right? So each of these values has a position in the input array. So how am I going to use the input array basically to tell us, for example, if I want to know in constant time if the value 2, right, the value 2, does 2 exist in our input array? How can I know that in constant time? The way I'm going to do it is I'm going to say, okay, we want to know if 2 exists. I'm going to take 2 minus 1, right? That's going to give us our index value. I is going to be 2 minus 1. We know that evaluates to 1. So we're going to go to the 1 index, right, which is over here. This is 0. This is 1. And we're going to go here and we're going to check, is this value negative? Negative tells us that 2 exists in our input array. We don't know where it exists, but we know that 2 does exist. We can figure that out in constant time, right? So we're going to use negatives to determine that. Just one problem. It turns out that this input array that we're given can have negative values by default. So how am I going to handle that? Well, it turns out we're looking for the smallest missing positive number. Obviously, by just looking at this, we know that that's going to be n equals 1. That's going to be the result, right? But we're looking for an algorithm to solve this problem. And it turns out that negative numbers are useless to us. We don't really care. If I took every negative number inside this input array and just crossed it out, it would not matter, right? So that's exactly what I'm going to do. I'm going to take every negative number, for example, negative 3, get rid of it, replace it with a 0. Why am I doing a 0? Why don't I just replace it with a 1, right? Well, in that case, if I replace it with a 1, I just changed the entire input array, right? Remember, the solution to this problem is n equals 1. If I add a 1 to this, then I've changed the solution to n equals 2, right? We don't want to do that. That's why we're giving it a neutral value of 0, right? I'm replacing every negative value with a 0. So it might be a little messy, but let's just assume that this has been changed to a 0. So we're going to basically scan through the entire array, change every negative value to a 0. We can accomplish that in O of n time, and we're actually going to be needing to scan through the entire array 2 more times. So it's overall going to end up being 3 times n, but that's still linear, right? That's still going to reduce to big O of n. And since we're not using extra memory, we're using the input array as extra memory, the overall memory complexity is going to be big O of 1. So now what I'm going to do is I'm going to start at the beginning of the array again, and now is when I'm going to start marking values as appearing in the array. For example, 3, right? We have a value 3. We want to mark that 3 exists in our input array. So what we're going to do is we're going to go to the index I equals 3 minus 1. That's index 2. Index 2 is over here, right? And we're going to change this value to a negative value if it's not already negative. Right now we see that it's positive, so what we're going to do is we're going to change it to negative, right? So we're just going to add a negative sign. This is going to be negative 6 from now on, right? So we are changing values, right? So it turns out that it's possible that this also could have been a negative 3, right? So basically every time we get to a value, we're actually going to be taking the absolute value of it, so absolute value of 3, and then minusing 1 to find the index. So since index 2 is negative, we know that 3 exists in our input array. Next, we're going to go to this value. It's 0, right? It turns out I equals 0 minus 1. That's going to be negative 1, right? That's out of bounds of our input array, right? That's going to be over here, right? That's out of bounds. So we're not going to be filling values that are out of bounds. So it turns out this is out of bounds. We're not going to fill it. Next, we get to the value 6, but remember this is negative 6 now because we changed it, so we're actually going to have to take the absolute value of this. Absolute value of negative 6 is going to be 6, right? So we're going to get I equals 6 minus 1. That's going to be 5, right? So again, we went out of bounds, right? That would be somewhere over here, but that's out of bounds, right? So and we know this would never be the solution anyway because it's too big. So okay, and then we're going to go to the last value. Again, we found a 3, right? So we're going to go to I equals 3 minus 1. That's going to be 2. We know index 2 is going to be over here. So, and we're going to change this to a negative, but good good thing for us, it's already negative. If it's already negative, we don't want to change it back to a positive number, because remember, 3 does appear in our list. Just because it appears twice doesn't mean we want this to be positive. We still want to know in constant time that a 3 exists in the input array. So we leave it negative. So then one last time, we're going to be iterating not through this loop. Now we're going to be iterating through this set. So we're going to be iterating through 1 through the length of the input array A, right? So that's also going to be an O of n operation, right? Basically the length of this input array. So we're going to start for n equals 1, right? We're going to take 1. We want to compute the index, right? So we're going to take 1 minus 1 is going to be 0, right? So we want to know, does 1 exist in our input array? We can check that by checking the 0th index of our input array. If it's negative, that means 1 does appear in the input array. If it's positive, which in this case it's positive, right? This is positive 3. That means n equals 1 does not appear in our input array, right? Therefore, n equals 1 is the smallest positive integer that does not appear in our input array. Awesome, right? That's the solution. We did that with 3 loops, but it still ended up being big O of n. There's one last edge case that I'm going to show you. Notice how this value was originally a positive 6, right? But we changed it to a negative 6 because we still wanted to know what value was originally stored here, right? So we could take the absolute value and then convert it to a positive 6, right? We wanted to know the original value. But we also wanted it to be negative so that we could indicate that a positive 3 exists in our input array, right? But my question to you is, what if the value that we're changing, for example, what if we had one more value in our input array and it was a 2? Then we want to mark that 2 exists in this input array. So we can compute I equals 2 minus 1. That's going to be 1. So we're going to go to the 1 index value in our input array, right? This is index 0. This is index 1, right? So now we want to mark that we want to change this to a negative value to mark that 2 exists in the input array. Hold on, this is a 0, right? But we don't like changing the value. We just want to multiply it by negative 1, but it'll stay 0. So what value can we change this to? For example, if I just change this to a negative 1, right, a negative 1 value, we can't do that. Why can't we do that? Because then we're changing the input array. Remember, this negative 1 will eventually, we're going to take the absolute value of the negative 1, right? And then basically we're assuming that a 1 exists in the input array, but originally there never existed a positive 1 in the integer array. So we can't change this to a negative 1. If we do that, we change the solution of this input array. So we have to change it to a negative value that does not affect the solution. But remember, the solution set could only be from 1 to the length of the input array. So if we change it to supposedly negative length of the input array plus 1, right? So basically we're taking length of the input array plus 1 and multiplying it by negative, right? If we do that, we're not changing the solution set, right? Well, actually, technically, this could be a solution, right? This would be the worst solution that it could possibly be, the greatest value it could possibly be. But notice with this value, it's out of bounds when we compute the index of it. So basically, this is a good default value to give it, because we're never going to be marking that value as showing up in our input array, because it's always going to be out of bounds. That's basically the point that I'm trying to make. So that basically handles all the edge cases. So if we found a 0, this is the negative value that we would give it to. Otherwise, we would just take that positive value and then multiply it by negative 1. So with all those edge cases being said, now let's actually jump into the code. It's going to be 3 linear time loops. So remember, the first thing I'm going to do is go through every value. And by the way, I changed the name of the input array to A just because it's shorter. We're going to be writing that a lot. I don't want to change it. I don't want it to be nums because I don't want to type that a lot. But I want to go through every single value. So for range of the length of this input array, if the value at that index is negative, remember, if it's less than 0, then we're just going to change it to be 0. That's a good default value to neutralize these negative values to. The next portion of this algorithm is going to be another for loop, just iterating through the input. I want it to be nums because I don't want to type that a lot. But I want to go through every single value. So for range of the length of this input array, if the value at that at that index is negative, remember, if it's less than 0, then we're just going to change it to be 0. That's a good default value to neutralize these negative values to. The next portion of this algorithm is going to be another for loop, just iterating through the input array, but this is the part where we're marking if a value exists in the input array or not. So we're overwriting the input array A. But remember, we're only doing that for values that are in bounds. So basically what I'm going to say is if our value at A at position I is, but remember, we're only doing iterating through the input array, but this is the part where we're marking if a value exists in the input array or not. So we're overwriting the input array A. But remember, we're only doing that for values that are in bounds. So basically what I'm going to say is if our value at A at position I, index I, is between 1 or the length of the input array A, if that's the case, so if this is the case, that means it's in bounds, but it could technically possibly be negative, because as we're going through the loop, we know we're going to be changing values to be negative. So we're going to take the absolute value of that, so absolute value of this, and we're going to store it in, let's say, value. Next, so we want to overwrite a position, right? So for example, we want to say A of value minus 1, right? Because we were taking the value, subtracting 1 to get the index. Right, so what we're trying to do is mark that this value exists. We're doing that by taking this and creating it to be negative. So what we're going to do is basically say multiply this by -1. But remember, we're only going to be doing that if this value is originally value -1, if it's positive, right? If it's positive, then we want to make it negative. If it's negative already, then we don't need to do anything. But the last case was else if this value happens to be 0, right? That was the edge case that we were worrying about. So if this happens to be 0, then what we can do is assign it to a special value of -1 multiplied by the length of the array plus 1. And that's actually this entire loop. So once this loop is done, we have basically, instead of using a hash set, we basically used our input array to mark which values between the range 1 to the length of the input array do appear in this array. So now we actually want to determine what the solution is. So I'm going to say for I in range from 1 to the length of the input array plus 1. Now we want to know if I does not exist in the input array. How do we know that? If A at index I minus 1, remember, so for any value, we're not exist in the input plus in range from 1 to the length of the input array plus 1. Now we want to know if I does not exist in the input array. How do we know that? If A at index I minus 1, remember, so for any value, we're subtracting it by 1 to correspond to the index. So if this happens to be negative, that means this value does appear. If it's positive though, or 0, if it's greater than or equal to 0, that means I never showed up in the input array. That means I was the smallest positive integer that did not show up, because we're going in increasing order, right? We're starting at the smallest and increasing. So if this is true, then we know that I never showed up, so we can return I as the smallest positive integer. If this entire loop executes from 1 to the length of the input array and we never returned anything, that means the smallest positive integer must be the worst case integer, which happens to be length of the input array plus 1. Okay, I'm really sorry, but I just noticed I had a bug. Remember, since A of I could possibly be negative, we actually want to compute the absolute value of that, A of I, before we check this condition, because if it's a negative number, then we want to take the absolute value before we determine if it's between 1 and the length of this. So really sorry about that. And instead of checking A of I, we're of course going to be checking the absolute value of that. So this is going to be the correct solution. Really sorry about the explanation, but I hope that most of the logic still makes sense of what we're doing. But this video actually took me longer than I expected, so let's wrap things up. This is the entire code. Like I said, we have 3 loops, so I hope that this was helpful for you. This is a linear time solution code. Like I said, actually took me longer loops for memory scribe. It supports the this is a
Let's code it. Okay, that's done. About it. Okay, so first iterate and mark the index, iterate and first remove, making them 0, 0. Next, nums of index greater than 0. Index plus 3 random value. Just that. -1. This value. So 341 3410. Continue. Greater than n. Okay. Greater than n-1. Continue. Is actually another. Continue. If norms of index is equal to 0, this first not equal to 0. Okay. Greater than 0, yes, it is greater than 0. Greater than 0. Greater than 0. Yes, this one is greater than 0. Come minus 1. Okay. Next, nums of I is equal to 4. Out of 4, if nums of greater than n, 4 is greater than 3. 4 greater than 3. I think we'll continue. Next, 0. 0. 0. 3. Instead of 0, can we just give it 1 plus 3? This should solve the issue. Still, okay. That's fine. That's fine. That's fine. This will become of index. No, it is not. Greater than 0, yes. Okay, minus 3. Minus 3, 4, 0. Minus 2. Index of 1 is 1. Yeah, exists. What is that? No. Um, into minus 1. Greater than 0. I, this should solve the issue.
Very continue. I'm doing index is equal to I minus 1. I drain I minus 1. What is wrong? Let us go back. As expected, this is the issue. हाँ मिल्क का चाय तागा मिल्क तागा వెనకాల వస్తున్నా Okay. Yeah, it's done. Took me 3 hours to solve three. Done with this. Now let's go towards a sprint. Um, what is this? Can tell a joke? It's easy. less than P2. No condition. I already know 2 pointers. I'm directly writing this. So given everything, then same one inside should be half. Return. Return. Sorry. Minus. Is there a way to stop? Run. Yes. This is the best approach. Okay, I think this complexity is like without this temporary. So how to switch without them. A is equal to A or B, B is equal to A or B, A is equal to A or B, A, B, A, A or B, A or B, A or B. Or A is equal to A plus B, B is equal to A minus B, A is equal to A minus B. A is equal to A plus B. Okay, like 5 is equal to 5 plus 6, 11. B is equal to 11 minus 5, right? A is equal to 11 minus 6. Pretty simple. Let's fix this. This is all two. P1 again, I know that. But yeah, I don't know. As not have it, I think just change this. Change this with this work. Okay, first thing, this is string, right? Sorry. Let's change it. What if it was absolutely right? How how is their complexity faster than mine? I don't think there's any better approach. Or I think this was terrific. This First, whatever. Probably they use this. See, the whole point of this question was not to use that. So, okay, I think it is done. That's actually okay, okay, okay. Let's progress. That's done. So we can solve four. Now valid palindrome. I think this part will struggle. That's fine. That's fine. Let's close this valid palindrome. I think I already solved it. Okay, this is a palindrome. Non-alphanumeric correct. Okay, actually, that's okay. Actually, I know this is very easy. I don't think it is hard. Uh, Remove. So this is easy. I guessed it, but let me see how it's approached by any code. Same.
Hey everyone, welcome back, and let's write some more LeetCode today. So today let's solve the problem valid palindrome. I'm actually going to be solving this two different ways, and I think both ways are definitely going to be helpful to know in an interview setting. Before we start, I just want to quickly mention that this problem is actually a part of the Blind 75 list of questions. And luckily, we have actually solved the vast majority of the Blind 75 questions. I even have a playlist of all of these questions in the description if you want to take a look. And of course, we will be finishing one more today, getting one step closer to 100% completion of Blind 75. So we are given a string S. All we want to do is determine if it's a palindrome. If it is, we can return true. If it's not, we return false. Only one catch is that we are only considering alphanumeric characters in the list, and we are ignoring cases. By ignoring cases, they mean upper and lower case. So false. Only one catch is that we are only considering alphanumeric characters in the list, and we are ignoring cases. By ignoring cases, they mean upper and lower case. So in the input string, you can see the leftmost character is capital A, the rightmost character is lowercase a. Both of these characters are considered the same. So if we had a string, an input string like big A, lower a, this string itself is a palindrome. So we do return true, even though one is uppercase and one is lowercase. A digit. So basically in this input string, it might not, because easy the same, and out is all will be non-alpha. So we have a version of this string, and the main way is going to be by using pointers. So we're going to have two pointers, a left pointer and a right pointer, because remember, there are multiple ways to check if a string is a palindrome. We don't have to reverse it. We can just compare the left character and the rightmost character. If they're equal, then we shift the pointers in, the left pointer comes here and the right pointer goes here, and then we can continue to check to make sure that the characters are equal. If they're not equal, then we return. But how do we know when to stop? Well, we're going to keep incrementing the left pointer, and we're going to keep decrementing the right pointer until eventually they meet in the middle, or the left pointer, passes the right pointer, right? The left pointer becomes here and the right pointer is over here. That's how we know when we can stop. Or maybe they will meet exactly at the same character if the length of the string happens to be odd. Okay, so that's actually pretty simple. Not too bad. So what are we going to do? Okay, left is here, right is here. This is capital A, but of course we're going to convert it to lowercase. This is lowercase a, so they're equal, right? Okay, so then right pointer is going to be decremented by 1. So the right pointer is going to be over here at the M character. Left pointer is going to be incremented. Nor try to do this, do that. Using ignore everything except base character. We're going to pointer is going to be decremented by 1. So the right pointer is going to be over here at the M character. Left pointer is going to be incremented by 1, and it's going to be here. Well, we're at the space character. But remember, we want to ignore spaces. We want to ignore everything except for alphanumerical characters. And can we try to do this without using a built-in function? Well, let me show you how we can kind of do that. Basically, I did some quick Googling, and we're actually going to use ASCII values to determine if a character is alphanumerical. Basically, what you need to know is that each symbol, ASCII symbols, is 128 of them, and lowercase and uppercase English characters happen to have an ASCII value associated with them. You can see the integer 0 has an ASCII value associated, 48. Integer 1 has 49, integer 2 has 50, so they are contiguous all the way down to integer 9, which is at 57. So that's important. And we also have uppercase A starting at 65, going all the way down to 90. They are contiguous as well. And then eventually we can get to lowercase, starting at 97, going all the way down to 122. These are contiguous as well. Using this information in pretty much every language, you can write your own alphanumerical character detecting function, and I'll show you how to do that in a few minutes. But for now, just assume that we do have our own alphanumerical function and our left pointer is over here. What do we want to do? We don't really want to compare this character with the character M on the right side, do we? Because we want to skip this character. So how do we skip it? Well, we can create a while loop. So while our left pointer is not alphanumerical, then we're going to increment left, right? We're going to do left plus plus. We're going to keep incrementing left while it is not a alphanumerical character, because we want to ignore characters that are not alphanumeric. So we're going to increment left one more time. Now, luckily, it is a alphanumerical character. It's the character M. So we compare left and right. They're exactly the same. So we continue with our algorithm. We decrement R over here, increment left over here. Right now they're both at the same character, and we're going to continue the algorithm. So that's the main idea. I won't run through this entire string because it's pretty long, but eventually the strings will meet in the middle. For example, over here somewhere, maybe. At that point, we'll see, okay, they're at the same character, and then we'll say we can stop our algorithm. We've determined it is a palindrome, and then we can return true. So now let me show you how to code it up. The benefit of this solution, it is still a linear time algorithm. It's still big O of n because we have to iterate through the entire string, but the memory complexity is big O of 1 because a dual parameter, just going to or not. How can we determine that? Well, I was using the ASCII values a moment ago. Right, I was talking about them. So in Python, you can get the ASCII value of a character using the ORD function. We just want to know that the ASCII value of this character, if it is an uppercase character. How can we check that? Well, as I showed you a moment ago, ASCII values are contiguous for uppercase characters, right? So from uppercase A to uppercase Z, they're contiguous. So if the ASCII value of the C character, of whatever this character happens to be, is between the ASCII value of uppercase A and uppercase Z, that means it's an uppercase character. So that's good so far, right? That's progress. For now, we can check that this is an uppercase character, but we want to check if it's alphanumeric. So we have to extend this idea. So how about we say, okay, that, or second condition, I'm actually just going to copy and paste this because it's going to be similar. We want to check if it's a lowercase character, right? Because that's the next thing.
All things are easy. Using ASCII value. Alrighty. I don't think we even need this script for anything. Uh, um, Lambda. So, Capital count as table as C. First capital, then small. Sha. CHR. Sha. should work. How can I block scope? confusing. Okay. Okay, good. This is correct. Four 483. P1 is 0. A naught A. Let's do this. So, input 0. Oh, like the symmetric shift. Okay. This is the exact two pointer approach. Done, 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 done. I think I'm done with half. So I think it's easy now. First three.
The sum so far is 3, right? So we to try that. Want to check?
Yeah, so P1 is 0. That palindrome 2. Come on, please, it should not be strings. String problem. This can be a random after living and not one character from it. Hmm. See if this can be a palindrome. First one character from it. Palindrome A, B, C, A. Match. Okay, let's go. Um, oh no, why is it even a zero? exception. X. False. Done. Example 3 is for how? I have to delete. It's slightly harder. Deleting one now. So we could either check one side or check the other side. Okay, it's fine. Like, this kind of addition. False. Okay, okay. 470. I think I'm written it true. So that is true. That a, a, guys is failing. Just over there. Is there? You should if it passes. Perfect, guys. Time it down. issue? What are the issue? Let's see the solution.
Hey everyone, welcome back, and let's write some more neat code today. So today let's solve the problem valid palindrome 2. We're given a string s and we want to return if it can be a palindrome if we delete at most one character. That doesn't mean we have to delete a character, but we can delete at most one character. So if you're familiar with palindromes, you should immediately be able to come up with a non-optimal solution for this problem, which is basically that given a string such as ABA, we know, to check that it's a palindrome is pretty easy. We just use a two-pointer technique, start at the ends, compare the two characters, they're equal, then we shift each of the pointers inward, and then continue that until we have no more characters left to check, or if maybe the pointers meet each other. So if both of the pointers in this case land at the middle character B, we know that it is a palindrome because of course they're pointing at the exact same character now. But it might not be a palindrome, but we're still allowed to delete one character. So if it turns out that the entire string is not a palindrome, well, the brute force would be to just, remove this character and check, is this a palindrome? Maybe it's not. Then remove this character and then check, is the remainder a palindrome, etc., etc. Now, if we do that, we'll have to potentially remove every single character and then go through the entire list each time. So that would be a big O of n squared time complexity solution, where n is the size of the input string. But it turns out that there is a better way. Suppose we had a string like this and then we start with the exact same two-pointer technique. Immediately would see that these two characters are not the same. But we also remember that we're allowed to remove one of the characters. Well, in this case, we know for sure that if it's possible to turn this string into a palindrome, we have to remove either this character or remove this character. Because remember, the two ends of the string have to be equal, but in this case they're not. So something has to change here, right? One of these characters has to change. The problem is we don't know which character has to change though. So technically we have to try both ways. We can first consider, let's say possibly this character can be removed, and then maybe is the rest of it a palindrome. When we do have the rest of the characters, we don't have to do anything fancy at this point because we already used up our removal. So all we have to check is this remaining string a palindrome? We know the algorithm to do that is very simple. And in terms of code, we can actually just take this string and then reverse it and turn it into ZZA and then check, is this equal to the original? Well, it's not. So that didn't work. So now we only have one option left. We have to check, can we remove this? And then is the remainder of the string a palindrome? Well, take the reversal of this. It is AAA. And yes, that's equal to the original string. So this way did work. We did find a palindrome. So then we can return true. But if it didn't work, suppose, this was an X or something, then this wouldn't be a palindrome either. And then we would have to return false. And it might not always be necessary that the two end characters are the ones that are unequal. It could be something like this, right? Initially, we would say, okay, these two characters are equal, right? So we don't have to look at.
Okay, I think I got my mistake. I did get my mistake, but uh, Well, ATBB Alibaba. TGAA. No, T and G is missing. Where's G from? BT? No. So, two, one. S of T1 is equal to S of T2. My God, why is it failing? unable to concentrate. Who if S of P1? Should work now. It's 95% finally done. LeetCode. 76. More than half is done. I think two more. After that, two SQL questions. That will be easy. Mars alternative, I don't think is hard. typical. Okay, we're going to string one string adding letters in alternate order. Append. Yes. Um, word on, word on. Nice done. Oh, guys, the strings. Come on, come on. Append. Plus, nah, plus. Click on merge. Mm, okay, next is merge sorted array. I think it is easy. I think I solved this. Come on, there is. Done. Why? 100% sort 8. Oh, 8 out of 10. Okay, I guess we'll do two SQL questions and we'll round it up. Leave this for tomorrow. 1, 2, 3, 4, 5, 6, 7, 8. Perfect. Now, time for SQL questions. We'll take some easy. Customize whenever. Customize. Okay. Orders. 1, 2, 3, 4. And the marks. Okay, I think I will select um, maybe from order from order from order where ID not no, okay. Where ID okay, cool. Three times consecutively. Hi, yeah, solid. Nine. Okay. with number window as just run, but I won't be running this. It's a bit hard. No, I won't be running this. Submitting that. Let's let's take another one. I think you have to select macro. Really? Maybe not. Okay, this is good, 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 good. Really, definitely directly to this now. Okay. Select one person. Right. Ah, right. Wait. Okay. Okay. Then start main map ID. is complicating it. Select P1 from person P1. And yeah, but no, delete P1 from person P1, join person P2 on P1 dot email, email and P1 dot email ID is greater than dot ID. Okay, I explain how does about P1 is a row you want to potentially delete. Okay. Delete. Um, yeah, I did understand this. I have to go through SQL once again. I think I'm done for today. Exhausted. Solved all three. So yeah, one time questions. So I guess I'm done for today. Exhausted. Yeah, let me see you guys tomorrow. Let's continue the answer. Oh yeah, before let's stop. Let's see how many problems. There's 82. There's 82. I just reloaded it once by mistake. 82. today we should be having 90. Okay, because there are repeated questions, so solved some repeated questions. So we have 92 submissions. Hmm. Aim for 100 tomorrow.